Welcome to Blacoh Session 2 on rainwater reclamation. I am Mark Girgenti. In the first part, we reviewed system sizing. In this section, what we're going to cover is what is in my water. It's going to be an in-depth look at rainwater, stormwater, and some of the other reclaimed water sources, and really what the contamination or potential contamination of those waters is, how to treat it, and then how to utilize it within your commercial building structure. So, what is rainwater? Most people really don't think about it, but in a scientific sense, rainwater is actually one of the cleanest sources of water available. Its hardness and sodium content is essentially zero. This is because it has no contact with the ground. There is no mineral content associated with it. It's not any kind of watershed. You just rain from the ground that hits your hand is a very, very clean source of water. It can be slightly acidic. This is due to its contact with atmospheric gases. Where I'm actually from the Northeast, our average rainfall is about pH 4.5 to 5 due to the amount of CO2 and hydrogen sulfide gas that gets in there, particularly from mining operations in the Mid-Atlantic region. But in general, rainwater can be acidic and also can be very basic. Down south, for example, rainfall tends to be far more basic in nature. It contains on average only about 2 to 20 parts per million of total dissolved solids. And comparing that to our municipal water sources, their total dissolved solids can be almost 40 times that value, 100 to 800 ppm. And again, this is because only real contact is with particulate matter found in the atmosphere, such as phosphates and other sulfates in the atmosphere. The problem is, once it hits the surface and I start collecting it, it is no longer a clean water source. And there are really 5 primary sources of contamination which can be found in both rain and stormwater. And again, stormwater in general is always more contaminated than rainwater. And these are metals, organics, bacteria and disease, turbidity, and then color. Metals, we're talking about things like zinc and lead. This is often found in the flashing material that's associated with roof construction. Organics, this can run the gamut from a lot of different things, from fertilizer to anything that could end up on your roof. Smog, as an example, is actually a particulate which can get dissolved into water. Bacteria and diseases from contact with animals, pigeons on your roof, birds. If it's a low-rise, if it's a single-floor building, you can have squirrels on there, things like that. Turbidity is just any kind of particulate that it picks up along the way. And then discoloration. This is oftentimes associated with dissolved metals in the water. One of the things that's hard, though, as an engineer is the building doesn't exist when I'm designing the system. So there's no way to take a water sample like you can from a well or from a city of water and look at what's in there when designing your system. You have to be able to almost foretell, based on a couple of parameters, what could potentially be in your water. Because again, until the building's actually built, there really is no way to ascertain that information. So there are really 4 different things to look at, which are going to have an impact on the level of contamination. This is really only for rain and stormwater at this point. The first one is geography. Where is my system located? I talked about briefly in the previous session about how geography plays into your rainfall, misting, heavy torrential downpours. Geography also plays into the level of contamination, and as does your rainfall. As I said earlier, in the Northeast, we predominantly have acidic rainfall. That's a universal. We never have basic rain, we always have acidic rain. As a result of that, any water we collect is a very acidic environment. Acidic environments are good areas for bacteria to grow. They also will cause a lot of metals to dissolve. Most transition metals, which is what you find, leads and zincs and coppers, all dissolve under acidic conditions because they themselves are actually metallic acids. In the Pacific Northwest, where they predominantly have misting rain, you really don't wash much contamination from your roof into those kind of situations. It's just this constant heavy mist. Almost think of like a steamer, for example, in a shower. You get that smear. You don't actually have anything really running down it. And then down south in the Gulf region, when they have very high levels of rainfall very fast, they wash everything down. Everything goes down there very, very quickly. In areas where you have very sporadic rainfall, you build up a lot of contamination. For example, in the southwestern region, you're going to see a lot more contamination in your captured rainwater because you have so much more time to build it up. So it's going to concentrate in your system. So geography does play a role in kind of the global look at what can be found in your captured rain and stormwater. Catchment surface elevation is obviously a little bit intuitive. I said earlier, stormwater and rainwater are differentiated because one is on the ground and one is a roof surface. And it's that perceived level of contamination difference between those catchment elevations, which is what leads to that change in classification from rainwater to stormwater. Stormwater catchment surfaces being ground level, you're going to have everything in there. You're going to have coffee cups, you're going to have antifreeze, you're going to have snow melt, you're going to have really almost anything that you can find littered on the ground could end up going into your system. When looking at a rain catchment surface, a first floor building as compared to a 30-floor skyscraper is also going to have a difference in what could be on that roof. The lower your catchment surface elevation, the higher the level of contamination. Because again, you're just closer to the ground. You're going to have more animals. You're going to have more particulate matter from the ground level based on winds than you will in a much taller building. So catchment surface elevation, the lower your catchment surface elevation, again, the higher the amount of contamination to be found in it. The third one is a little bit less intuitive, and that's looking at the general region where your system is going to be located. I'm not talking about geography. I'm not talking about my Pacific Northwest, Northeast, Gulf region. I'm talking about, are you in a metropolitan area? Are you in an agricultural area? Are you in an industrial area? Are you in a wooded area? Again, within kind of like a 20-mile radius. Are you on the shoreline? These kind of local kind of microcosms have an impact on your system. To give a couple of examples, if I'm in the middle of New York City, I'm gonna have a lot of smog on my roof. If I'm in the middle of Kansas, I'm gonna end up with crop dusting on my roof. I'm gonna have a lot of fertilizer. If I'm in the Gulf Coast region, I'm gonna have seawater splash, sea spray on my roof. Actually, a fairly famous case that happened a few years ago was they actually found Legionella in rainwater. And that was actually traced back to a result of marina washing. They were washing the boats in the marina. That water was misting onto the roof that was then being captured, and they actually had a Legionella outbreak in that case. Again, it was a southern region. Rainwater itself doesn't have Legionella in it. Again, that's only in standing bodies of water, but that contact with that mist from a standing body of water led to that local level of contamination. If I'm in an industrial area, whatever industrial byproducts, as I said before, even on a larger scale, the reason the Northeast has acid rain is because of coal mining. The coal mining in the Appalachian, the hydrogen sulfide gas is what leads to our acid rain. All of that soot in that area is going to end up now on all the roofs in that area. So it's a little bit less intuitive, but looking at kind of what's in that sort of 20-mile radius around your roof is also going to play into a lot of different contamination that could be found on your catchment surface and then also into your collected rainwater. And then finally, what the material construction of your roof is. Is it metallic? Is it ceramic? Is it tar? Is it pebbles? There's a lot of different things, and what those are can leach into your rainwater. If you have a metal system, for example, copper and zinc or lead, they did an analysis actually out in Seattle, Washington a few years ago where they looked at, really is there higher concentrations of things like lead that's used very often in in copper, in flashing and roof construction in rainwater, and they did find appreciably higher ppm levels of things like lead in rainwater from metallic roofs than they did in other types of roofs. So what your roof's also made out of also has a fairly large impact on your water system. It should be worth noting that, as I said before, rainwater and stormwater treatment systems are almost universally in the US only used for non-potable systems. So talking about water contamination, like why do we really treat the water? A lot of it is because, again, if I'm using a flushing fixture, all water in a flushing fixture, regardless of source, is black water. But what you're understanding is you are moving this water around your building. You are using it for things like irrigation. You are putting it, so if you have discoloration, you have metals, things like that, you are still transporting now a waste from your system to your use, which is a lot of the reason why we treat this water ahead of time, not to any kind of potable levels. That's one of the things that's interesting to note too, is there really isn't a set standard for water quality. They are starting to come out with them. They look at things like TDS, total dissolved solids, as I said before, things like that, but there is no specific quality for rainwater or stormwater for use, and there isn't really a way to empirically determine what levels of contamination are found in your various water sources. So it's because of this kind of guesswork that we use these types of parameters when we help us design our system. So what we're going to look at now is how do we really design a rain/stormwater harvesting and treatment system. Rainwater and stormwater treatment systems ideally begin the treatment right at the catchment source. In talking about what potential contamination can be found in both rain and stormwater systems, one of the things I highlighted is that everything is based on what's on your catchment surface. Well, those of us who have driven on roads know that when it first starts raining on a road, the road is kind of slippery. That's because of all the rubber buildup and oils from the cars going over it over time. After about 5 or 10 minutes of raining, the road isn't slippery anymore because I've washed away all of those contaminants. Ideally, from a treatment standpoint at your catchment surface, you want to divert that first 5 or 10 minutes of rainfall away from your cistern tank. That'll help mitigate quite a bit of those potential contaminants that you're going to find on your roof surface. There are a couple of devices out there to do this. Unfortunately, and this is one of the things to understand when you're talking about any kind of rain or storm water system, a lot of these technologies were originally developed for residential applications, so they don't really work in a commercial system. So they did develop technologies such as I have here, which are like flush devices. They take the water coming in, and based on a float mechanism, they divert that first flush, they divert that water away. The problem is they're only sized for very low flow rates because they're designed to go in somebody's house. There have been steps to modify and use some of this equipment on more of a commercial building scale, but they're not at this point really rated for the pressures. So what people are turning to is proving commercial technologies. Another very common system people like to use is what's called a Vortex Filter, where the water comes in, under gravity, you basically self-clean the filter. You divert any kind of heavy debris away, and you allow anything above 500 microns to go into your system. The problem with most of these commercial vortex systems out there is that they're designed for very low flow rates, which is only up to maybe 250 gallons a minute at fairly low pressures. If you're talking about a building which is 10 stories tall, and the water comes down, you're going to basically destroy the system. They're just not designed for that kind of pressure, and they're really not designed for very high flow rates that you typically see in commercial buildings. So people are using things like, now they're developing like concrete separators, they're converting basically oil-water separation systems and now being utilized for rainwater systems. So good concepts that are still being developed into adequate technology, but really the point of any kind of treatment at your catchment surface is to, one, either avoid transferring water to your system during that initial surge of rain, and to remove any very large contamination. In this case, I'm talking about particulate matter turbidity. You're not going to be able to remove bacteria or discoloration or any of those types of contaminants at the roof surface. You have to do that in your actual treatment system. Moving from the roof catchment surface, and even actually after the cistern, the third and arguably most critical facet of a rainwater system is the actual rainwater treatment system. And at a minimum, does particulate filtration, disinfection, non-potable identification, and water repressurization. And there are two different styles of treatment systems, and they're differentiated by how they interact with the cistern tank. There's what's referred to as a cistern storage system, and then what's referred to as a direct storage system. In a direct storage system, this is probably what most people think of when they think of a rain or stormwater harvesting system. I have my rainwater catchment surface. I have my cistern tank that we discussed in the first session. You pump through the treatment system directly to your point of use. This is a good situation when you have very low flow systems or when your treatment system is not very complicated. If you have very complicated treatment systems, the higher the flow rate through them, the more cost and more energy and more resources are associated with now what's becoming a green technology. The Cistern style system essentially utilizes a 2-tank configuration. I have my rain catchment, rain or storm water catchment. I go into my cistern tank. I then pump from the cistern tank through the treatment system to now a clean water storage tank. And then I repressurize from that for building use. This is a good setup when you have very high instantaneous demands like you'll see in a flushing fixtures. If I'm in a high rise, for example, I can have 300 gallons a minute instantaneous flow rate. But I really don't run that for more than a couple of seconds. So I can then transfer through my treatment system at like 50 gallons a minute, a much, much smaller flow rate than downsizing my system. This is also good when you have combined water systems. If you're talking about taking rainwater with, for example, like reverse osmosis reject water, you sometimes cannot combine those two together in the outside rainwater cistern. That's a code issue where you can't discharge non-storm water down the storm drain. So they end up combining them then downstream in a clean water storage tank. So you can, if you have two different water sources, this is also an ideal setup. And if you have very complicated treatment, so you have to go to like a membrane or some other treatment system, you really want to keep those as small as possible, so you do want to utilize the 2-tank design at that point. Particulate removal is the first step of any rain or storm water treatment system. And the ideal range that you're treating to is about 50 microns. When you're talking about the upstream of the cistern, you're talking about from your roof catchment, you're really talking about like 500 micron at this point. At this level, you're looking between 50 and 10 micron. The reason some people use 10 micron filtration is because at 10 micron and below, you're removing any kind of film buildup that could develop downstream of your piping system. If you're going into potable water, you need to use a 1 micron absolute filter, NSF approved, National Sanitation Foundation. There are a couple of different styles of filters which are used. You have your classic bag or cartridge filter set up, but a lot of people are going into low flow backwashable filters. Multimedia filters are not ideally situated for this kind of use because they have very high backflush. People are using devices like automatic screen filters or spin disc filters, which utilize very low flow and actually utilize reclaimed water themselves for their backflushing process. This is to mitigate a lot of the maintenance required for these systems. Again, these systems are not necessarily going into an industrial building or something like that. They could be going into a high school, as an example, where you're going to have a janitor washing the system. You don't want to be using a very high maintenance device. You want to use a simple system that really requires very minimal maintenance in those cases. Carbon filtration is sometimes utilized in rain and storm water systems. What carbon does, carbon is essentially a large graphite sheet base where they're basically pulling out different organic compounds in there. This is a very case-by-case basis. You don't see this too often in rainwater systems. You don't see a lot of organics buildup unless you have a very specific regional development for it, or if you're using it for potable. In potable, you're going to use this to remove any aromatics from the waters, which help improve taste. But generally speaking, utilizing a carbon filter is not a necessary filtration step for rain or storm water reclamation systems. Disinfection is very central though to these systems. As I said, you're going to come in contact with the surface on outside, which can have a lot of different contamination on it. For rainwater, it could be things like leaves and bird feathers and a lot of other types of organic matter. For a stormwater use, I can have somebody's coffee cup going down into there. There can be very heavy amounts of biologics that can be found in these systems. And there's really two schools of thoughts on disinfection. The first is to use UV or radiation sanitization, and the second is chemical sanitization. I personally prefer UV sanitization. What you do is you basically use ultraviolet radiation. It's in the UVC range, which is 254 nanometer UV. It's not the light you see in a tanning bed or outside. This is what you see in the upper atmosphere. And at that wavelength, you can break down bacteria. And your intensity for this light is typically fairly high, about 30,000 for these different types for rainwater systems. The benefit of UV is that you're not introducing any kind of chemicals into your water, like chlorines or things like that, which could invariably cause problems with downstream chemically sensitive components such as cooling towers, or if you're using it for irrigation, you don't want to be spraying chlorine onto your plants. Chlorine is used in some applications. The downside to chlorine is, one, I now have a chemical that I'm introducing into my system. I also now have to have somebody actually watch this. Now, of course, I'm taking what is relatively considered a green process, and I'm introducing this now chemical to it. It also requires a fair amount of contact time. One of the things people don't realize is you can't just throw chlorine into water and it's instantly clean. Think about it, anybody here owns a swimming pool. If I sit there and throw chlorine into it, I have to wait overnight, and then the water, it looks clear. That's because there's a lot of residence time involved in the reaction for chlorine to actually act as a disinfectant in this case. And again, also is not ideally suited for some uses for rainwater, such as irrigation. Its one benefit over UV is that it has residual contact time. If I chlorinate something, it can stay clean for as long as the chlorine is still in the solution. The problem with UV is once I pass through it, if I reintroduce a contaminant into my water stream, I now have a situation where there is no residual treatment. You pass through the UV, it's a one-shot kind of deal in that case. So you have to look at what is ideally best for your application with a chlorine or UV sanitization. Kind of as a side case here, Legionella, as I mentioned in that one example before, when we were talking about what could be in your water, Legionella is not found in rainwater systems, generally speaking, because Legionella is found only in standing bodies of water and only propagates at very specific conditions, which are typically about 90 to 95 degrees Fahrenheit, or that's why you see them a lot in hot water loops, for example, in hospitals, places like that. I mention it here because a lot of the sanitization devices which are used for rainwater are not effective in Legionella removal. So generally not a concern. It can be a concern more in stormwater, where you can have a lot more contact with standing bodies of water or ground level bodies of water in those cases. Rainwater, depending on where you are, can definitely have different pHs. As I said before, I'm from the Northeast. We have rainwater that's about pH 4.5 to 5. That's pretty low. That's why if anybody's ever been in an old building on the East Coast, you're gonna notice a lot of blue on all the copper piping in the building. That's all copper sulfate caused by the sulfuric acid in the rainwater. You really ideally don't want that. You really want your rainwater ideally to be neutral in pH. This will prevent metal contamination from your roof from getting in, also prevent damage to a lot of your downstream piping in the system. If you have any metal, or if you're using it for flushing fixtures, any kind of copper or brass you use in your actual flushing fixture header. Rainwater is almost exclusively always acidic. The reason being is there is no gaseous base that's going to be found in the atmosphere. Base actually goes through a solid, whereas acid goes through a gas when it changes out of a liquid state. So you really only need one-way adjustment in these cases. You want to ideally raise the pH. This can be done with controlled chemical injection, or it can be done with what's called a passive system. They use things such as limestone as an example to help raise the pH to a neutral value. As I mentioned in the cistern design, you are introducing a secondary tank into your system called the clean water storage tank. And the clean water storage tank serves a very similar purpose to your cistern and follows a lot of the same rules for cistern design that we talked about in session 1, except it's considerably smaller. You know, whereas a cistern could be 10,000, 50,000 gallons, your clean water storage tank is going to be about 100 gallons, 500 gallons, or 1,000 gallons. It's almost always inside, right next to your actual treatment system. It should always be pigmented. Now that you're inside, you're under lights, you know, the temperature is much more controlled, it can be very warm. Pigmentation will help prevent any additional bacteria growth from occurring within that system. But ideally, it's really nothing more than a thermoplastic tank in most cases, a fairly simple addition to your system. Non-potable identification has been around for a fairly long time in rainstorm water systems, and a lot of the reasoning behind that is because a lot of these were originally all kind of classified together as gray water at one time. Even though now we know them as a different setup, they are ideally situated, they were originally looked at as a gray water or even as a health code source. As a result of that, people have developed a couple of different means for identifying the water that's going to be used as a non-potable source. The most common one is the injection of purple, that's really blue, dye into your system. And here you can see what it looks like at both full concentration as well as in more dilute, which is what you typically see. It kind of looks like you put bleach in your water effectively at that point. That's to identify it as a non-potable source. And the reason they do that is not because anybody's going to actually drink out of a flushing fixture, but say 10 years from now, when somebody taps into a line, maybe runs into a water fountain, they turn it on, they start shooting blue water out, that gives them a heads up that this water is probably not ideally lined to a drinking fountain in that case. It actually did happen at a high school in the Midwest about 10 years ago. They actually ran the blue line right into it because people use other means. They use purple piping. One of the means they spray paint things purple, always identifying it as a non-potable water source. In states such as Washington and Oregon, where they actually allow potable, they have a little more extreme measures for identifying the rainwater as a non-potable source. And these largely include putting things like signs. So if you ever walk around an area in Seattle, Washington, and you see a sign on a toilet that says "do not drink," that's because of the identification codes. Not that dogs can read, but they do end up doing that all the same. That's really governed by what your local codes are. There really is no universal standard for that. It depends on what you're using it for as well. If you're using the water for irrigation, you don't have to dye the water because obviously we don't want to spray all the plants purple or blue in this case. And that is nothing more than a food dye. It's very similar dye to what they actually use to dye the water green in Chicago on St. Patrick's Day. It's the same kind of water in that case. As mentioned before, a lot of times people use what's called combination systems. Rainwater and stormwater reclamation in general is unpredictable because it's a precipitation event. You could have all your rain in a 1 week period and then have no rain for 4 weeks. You could have nice spaced out storms. Or if you're in certain areas of the country, you really just don't have a lot of rainwater to actually reclaim. As a result of that, they use what's called combination systems to create a more complete picture or to help subsidize the water use in your building. They look to sources such as, again, stormwater, gray water, and other clear water sources such as reverse osmosis or cooling tower reject water as an additional source. Stormwater people do separate from rainwater a little bit because, again, given the there really is almost no time you want to use stormwater unless you really need that extra volume. It's in some ways worse than other other rainwater sources because once you start introducing things like antifreeze into your water and stuff like that, your level of contamination is just so much higher in those cases. When doing this, a lot of the same types of technologies we just talked about still apply. You have your filtration, you have your disinfection, you have your non-potable identification, but you need to add in additional treatment steps into these cases because these waters now have completely different characteristics than what rainwater would have in general. So for things like stormwater, again, as I said, you're gonna have oil. So the first thing you have to do is take any oil separation out. You're gonna have antifreeze, you're gonna have other types of heavy loading bacteria in your system. For cooling towers, you're gonna have very high mineral content. One of the reasons cooling towers blow down is based on conductivity. The higher the conductivity of the water that causes it to blow down. There's also very high bacteria and other chemicals like biocides, which are introduced into your cooling tower as a means to keep them running. So all of this stuff is gonna have an impact into your water system. Hvac condensate is a very clean water source, but it's also a very low quantity source. Nothing really more than condensation of moisture found in the air. RO, or reverse osmosis reject water, is very similar to city water, except it's gonna have about 4 times the amount of total dissolved solids in it. So if you have 800 ppm, you're not gonna have 4,000 ppm or higher, and that can lead to a lot of scaling issues and a lot of misuse for systems. And then finally, gray water, as I said before, not an ideal candidate based on its very low water quality, very high bacteria. You have surfactants, you have foam, you really don't want to use this unless you really have to in those cases. And that's kind of a whole separate conversation is how you really treat gray water systems in that case. So when using combined water systems, there are other types, you have to do some additional treatment in these cases. For parking lots, you want higher UV doses, combined with secondary chemical treatment. You're gonna need oil and emulsion separation. Cooling towers use membranes to help remove the TDS, pH adjustment, and then descaling agents. HVAC really is very clean, but again, very small. RO reject is going to have a lot of scaling issues, and then for gray water, you're talking about a lot of different chemicals, biological treatment devices like that. Really is almost secondary and tertiary if you're familiar with large-scale wastewater treatment systems, like municipal levels of treatment for those types of systems. If you're using stormwater in place of rainwater, you really kind of ignore all that stuff about roof catchment surface and filters, and you really go into more oil-water separation. You're gonna have to, first thing you have to do is remove all the oil, antifreeze, and other chemicals which are gonna run off from your stormwater source. And these kind of act as your pre-filter in those cases. So these may or may not be emulsified. Emulsified essentially is a substance which is not dissolved, but basically is chemically bonded to water. So you see oil-water emulsion, you cannot physically separate it, so they do use what's called an emulsion breaker in a lot of those cases then to break that kind of oil-water bond. Antifreeze does that a lot. You probably see a very kind of pretty color on the ground. That's because it's emulsified now in the water. You need to actually separate that and then take it out of your system prior to use. Membrane filtration is really a higher form of filtration than what we talked about previously, about 10, 50 micron. In membrane filtration, I'm really going to the submicron level. I'm going down to things as low as 0.0001 micron filtration, in the case of an ultrafilter, or even as far down as using a reverse osmosis system itself. And in both these cases, you're really repelling your viruses, your bacteria, all your suspended solids, and a lot of your dissolved solids, only letting through some very small things, monovalent ions, things like that. In the context of cooling towers and even some rainwater applications, people do use membrane. It's also very commonly used in groundwater treatment. One of the things that's also coming up a lot more now is reclaiming groundwater. For a long time, people who were putting in buildings, putting in foundations, they were just allowed to pump all the displaced groundwater right to drain. Now a lot of municipalities are requiring them to reuse that water, and that water is going to have very high mineral content, because again, it's not like well water, it's very high level subsurface groundwater. For example, like down in Washington, D.C., the Potomac River basically floods out that entire area. Any building you put in, you're displacing a lot of water in those cases, and you need membranes to help remove that very high ionic content. It's also the only type of filter which can remove discoloration. There's no other means of removing discoloration from the water without going to a membrane level treatment system. So for those who don't understand, for those of you who don't know reverse osmosis, what it is, I'm essentially applying a very high pressure across a membrane, and I'm moving water against the osmotic gradient. So I'm moving from an area of high solute concentration to an area of lower solute concentration, which is otherwise termed reverse osmosis. And by doing that, I'm getting very, very fine filtration. We're talking about down to the ionic level at this point. So to summarize combined water systems, they have a lot of benefits. They give you a much better water profile for use, but they also may require a lot of additional treatment or add additions to your system. It's also important when looking at combined water systems to match them, whatever their water source is, whatever their particular contamination level is, to what you're using it for. So cooling towers is an example. They want water with very low conductivity. Using reverse osmosis reject water is a bad alternative for cooling towers, because now you're taking a water with very high conductivity and you're using it in cooling towers where you're going to cause them to blow down more frequently. On the converse side, irrigation actually likes that very high mineral content because it acts as a fertilizer. So kind of matching them to their right water source is also important when combining them with a rainwater or stormwater harvesting system. So to summarize this second session, what we really discussed is how rainwater is contaminated, how you determine that level of contamination, what different types of systems are available, both direct and then cistern storage systems. Talked a little bit about roof catchment, and then we talked about treatment within the actual rainwater or stormwater treatment system. We then ended off looking at combination water systems and the additional treatment options which are involved in those. In the next session, what we're going to do is we're going to take the first all the information from this, and we're going to look at a couple of real-world problems, and we're going to design treatment schemes for those, as well as going back to the first session, we're going to look at an actual water sizing profile to create a complete picture of how you fully design and integrate a rain stormwater, as well as a combination rainwater combination system as well.